Imagine traveling for 49 years, not through cities or countries, but through the unimaginable vastness of space itself. Imagine journeying so far from home that Earth becomes nothing more than a pale blue dot, a single pixel suspended in a sunbeam. Imagine crossing distances so extreme that when you send a message home, it takes an entire day for your words to arrive. Traveling at the speed of light itself, now imagine what you might find out there, in the lonely darkness at the very edge of everything we've ever known. What lies beyond the protective embrace of our sun? What marks the boundary between our solar neighborhood and the vast, alien territory of interstellar space? The answer is more stunning than anyone expected: a blazing barrier of plasma so hot it's been called a wall of fire, a region where temperatures soar to a staggering 30,000 to 50,000 Kelvin. That's 54,000 to 90,000 degrees Fahrenheit hotter than the surface of most stars. Welcome back to the Cosmic Altis, your gateway to the most incredible discoveries in space exploration. Today we're diving deep into one of the most extraordinary findings in the history of space science. This is the story of how a tiny spacecraft, launched when disco was king and the Cold War still raged, became humanity's first ambassadors to interstellar space and discovered something that has fundamentally changed our understanding of where our solar system ends and the rest of the galaxy begins. Before we embark on this cosmic journey together, I need your help. If you're fascinated by space exploration, if you've ever wondered what lies beyond the known boundaries of our solar system, then hit that like button right now. It helps this video reach other space enthusiasts and supports our mission to bring you the most in-depth space content on YouTube. Subscribe to the channel and smash that notification bell so you never miss an episode. We're building a community of cosmic explorers here, and you're invited to join us. Share this video with anyone who's ever looked up at the night sky and wondered what's out there. Because what we're about to discuss isn't just scientifically groundbreaking, it's philosophically profound. Here's what we're going to explore together in this deep dive. First, we'll travel back to 1977 and witness the birth of the Voyager mission. How a rare planetary alignment created a once-in-176-year opportunity, and how NASA built a spacecraft designed to survive the impossible. Then, we'll follow Voyager's journey from the giant planets to the very edge of the sun's domain, understanding what it means to reach the edge of the solar system, a concept more complex and fascinating than you might imagine. We'll witness the historic moment when Voyager crossed the heliopause, the true boundary of our solar system, and what the spacecraft detected as it passed through this cosmic frontier. Next comes the main event, the discovery of the Wall of Fire, a superheated plasma region that defies expectations and reveals the dramatic collision zone where the sun's influence meets the interstellar medium. We'll explore what these discoveries mean for understanding our cosmic neighborhood, how the heliosphere protects us from deadly galactic radiation, and what implications this has for future deep space exploration and human missions beyond Earth orbit. Finally, we'll check in on where Voyager is now in 2026, how much longer these incredible machines will survive, and what comes next in humanity's quest to explore interstellar space. But here's what makes this story truly extraordinary, and why I'm excited to share every detail with you today. This isn't ancient history. This is happening right now, as we speak. Voyager 1 is approaching a distance of one light day from Earth, a milestone it will reach in November 2026. That's just months away. When that moment arrives, any command we send to Voyager will take a full 24 hours to reach it, traveling at 186,000 to 182 miles per second. And then we wait another 24 hours for a response. The Wall of Fire discovery has been confirmed by multiple measurements from both Voyager spacecraft, using instruments designed in the 1970s but still revolutionary in what they've revealed. The data continues to pour in, even now from 15.8 billion miles away, rewriting our understanding of the solar system's edge. But perhaps most remarkably, this discovery forces us to confront a profound realization. We live inside a protective bubble, a magnetic cocoon created by our sun that shields every planet, every asteroid, every living thing on Earth from a universe filled with deadly radiation. Without this heliospheric shield, life as we know it will be constantly bombarded by galactic cosmic rays powerful enough to sterilize planetary surfaces. The wall of fire marks the boundary of our safety, the edge of our cosmic shelter. Think about that for a moment. Everything you've ever known, every human civilization, every species that's ever lived on Earth, every thought ever conceived exists within this bubble. And we're only now, in the 21st century, just beginning to understand it. Are you ready to journey to the edge of everything? Are you prepared to understand what lies beyond the boundary of our solar home? Then let's begin this incredible voyage together. The journey starts not in the depths of space, but here on Earth in the year 1977, a time when humanity was about to launch the tiny messengers that would forever change our perspective on our place in the cosmos. To understand the magnitude of what Voyager discovered at the heliopause, we first need to appreciate the audacious vision that birthed this mission and the extraordinary circumstances that made it possible. The story begins with an alignment, not a political alignment or a technological breakthrough, but a literal celestial alignment, a cosmic choreography that occurs once every 176 years. In the late 1970s, the four giant planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, would arrange themselves in a specific configuration that would allow a single spacecraft to visit all four using a technique called gravitational assist, or the gravity slingshot effect. This alignment was recognized by a young aerospace engineer named Gary Flandro at NASA's Jet Propulsion Laboratory in 1965. Flandro calculated that a spacecraft launched in 1977 could fly by Jupiter, using the planet's immense gravity to increase its velocity and redirect its trajectory toward Saturn. Then Saturn could fling it toward Uranus, and Uranus toward Neptune, each counteracting like a cosmic slingshot, accelerating the spacecraft without using additional fuel. This trajectory, which became known as the Grand Tour, would take approximately 12 years, far faster than the decades required if a spacecraft had to use its own propulsion to reach each planet individually. Without this fortuitous alignment, exploring all four outer giants would have been economically and technologically impossible. With 1970s technology, time was of the essence. The launch window would last only a few years. Miss it, and humanity would have to wait until the year 2153 for another opportunity. NASA moved forward with an ambitious plan: build two identical spacecraft with redundant systems, pack them with scientific instruments, and send them on humanity's most ambitious planetary tour. The spacecraft themselves were marvels of engineering. Each Voyager weighs approximately 1,820 pounds, 825 kilograms, and stands about 8.5 feet to 0.6 meters tall. The most distinctive feature is the 3.7-meter 12-foot high-gain antenna golden dish that would serve as the spacecraft's primary means of communicating with Earth across billions of miles of space. But how do you power a spacecraft designed to operate for decades in the outer solar system, where sunlight is too faint for solar panels? The answer: radioisotope thermoelectric generators, or RTGs. Each Voyager carries 3 RTG units containing plutonium-238 dioxide. As the plutonium naturally decays, it generates heat, which is converted into electricity through thermocouples. At launch, the RTGs produced about 470 watts of electrical power, roughly enough to power for standard household light bulbs. This may not sound like much, but it was sufficient to power all the spacecraft's instruments, computers, and communication systems. The genius of this design is its longevity. Unlike solar panels or chemical batteries, RTGs could continue generating power for decades. Even now, in 2026, nearly 49 years after launch, the RTGs still produce about 240 watts, enough to keep critical systems operating. The scientific payload was equally impressive. Each Voyager carried 11 scientific instruments designed to study planetary atmospheres, magnetic fields, rings, surfaces, moons, and particles in space. These included Imaging Science System ISS to television cameras, one wide angle, one narrow angle for capturing detailed images of planetary systems, plasma science experiment, measuring charged particles in the solar wind low energy charged particle instrument, detecting ions and electrons cosmic ray subsystem, studying high-energy particles from outside the solar system magnetoma, measuring magnetic field strength and direction planetary radio astronomy, detecting radio waves emitted by planets' plasma wave subsystem, measuring plasma waves, and electron density ultraviolet spectrometer, analyzing ultraviolet radiation from planets. These instruments, designed primarily for planetary encounters, would later prove crucial for detecting and characterizing the heliopause, a mission extension never imagined during the design phase. Now, let's talk about the most poetic element of the Voyager mission, the golden record. Each Voyager carries a 12-inch gold-plated copper phonograph recorder message bottle, cast into the cosmic ocean, carrying the story of humanity to whatever intelligence might one day find it. The record's contents were curated by a committee chaired by the legendary astronomer Carl Sagan. It contains greetings in 55 languages, from ancient Sumerian to modern Mandarin sounds of Earth, whale songs, wind, thunder, birds, laughter, human heartbeat, a kiss, footsteps, fire, and the first tool's 90 minutes of music from cultures around the world. From Beethoven's Fifth Symphony to Chuck Berry's Johnny Be Good, from Giovanni's Gamelan to Peruvian, Panpipe's 116 images encoded in analog form, showing mathematical definitions, human anatomy, DNA structure, continental drift, human architecture, and snapshots of human life. One of the most profound messages came from then UN Secretary-General Kurt Waldheim. I send greetings on behalf of the people of our planet. We step out of our solar system into the universe seeking only peace and friendship, to teach if we are called upon, to be taught if we are fortunate. The record also includes instructions on how to play it, with the stylus included for any civilization that might intercept it. The cover features symbols showing the record's location relative to 14 pulsars and our sun, a cosmic address, written in the universal language of physics. Carl Sagan wrote movingly about the golden record. The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The launch sequence unfolded like this. Voyager launched first on August 20th, 1977, atop a Titan E Centaur rocket from Cape Canaveral, Florida. Counterintuitively named, Voyager was designated as such because it would follow a slower trajectory and arrive at Jupiter after Voyager 1. Voyager 1 followed 16 days later, on September 5, 1977, on a faster trajectory that would allow it to reach Jupiter and Saturn before its twin. Despite launching second, both launches were picture perfect. The spacecraft were on their way, carrying humanity's hopes, curiosity, and greetings into the cosmic unknown. The primary mission objectives were clear: conduct close-up studies of Jupiter and Saturn, their rings, atmospheres, and magnetic environments above the moons of both giants, particularly Saturn's moon Titan, which was suspected of having a substantial atmosphere. Voyager 1's Saturn encounter was successful. Voyager 2 would continue to Uranus and Neptune. Planetary encounters exceeded every expectation. At Jupiter 1979, the Voyagers discovered active volcanoes on the moon Io, the first volcanic activity detected beyond Earth. They found evidence of a subsurface ocean on Europa, revealed intricate details of Jupiter's ring system, and captured stunning images of the Great Red Spot. At Saturn 1980-1981, they revealed the complex structure of the ring system: thousands of individual ringlets, braided rings, and mysterious spokes. They discovered new moons and provided the first detailed study of Titan's thick, hazy atmosphere. Voyager continued to Uranus 1986, revealing a planet tipped on its side, with a magnetic field dramatically offset from its center of planetary oddity. That still puzzles scientists today. Finally, at Neptune 1989, Voyager completed the grand tour, discovering that Neptune's atmosphere harbored the fastest winds in the solar system, and that its largest moon, Triton, had active geysers of nitrogen gas. But the story doesn't end there. After completing their primary missions, both Voyagers were still functioning, still powered by their plutonium hearts, still capable of science. NASA made a bold decision: continue the mission into interstellar space. This extended mission, officially designated the Voyager Interstellar Mission VIM in 1990, had a new objective: study the outer reaches of the heliosphere and, if possible, cross into interstellar space itself. No spacecraft had ever attempted this. No one knew for certain what lay beyond the heliopause, or even where exactly it was located. The Voyagers would be pioneers in the truest sense, venturing beyond all maps, into territory never before explored. The journey to the edge was about to become even more extraordinary than anyone imagined. After Voyager 2's Neptune flyby in August 1989, the final planetary encounter of the Grand Tour, both spacecraft found themselves in a region of space no human-made object had ever explored. Behind them lay the familiar realm of planets, moons, and sunlight bright enough to see by. Ahead lay the unknown. But what exactly is the edge of the solar system? This seemingly simple question has a surprisingly complex answer, because the solar system doesn't have a single, definitive edge. Instead, it has multiple boundaries, depending on what you're measuring. Let's explore the different ways to define the solar system's edge. 1. The orbital definition. If we define the solar system by the orbits of major planets, it ends at Neptune, approximately 30 astronomical units from the Sun. 10, or astronomical unit, equals the distance from Earth to the Sun, about 93 million miles or 150 million kilometers. 2. The Kuiper Belt. Beyond Neptune lies a disc-shaped region populated by icy bodies, dwarf planets like Pluto and Eris, and countless smaller objects, the remnants of solar system formation. This extends from about 30 astronomical units to roughly 50 astronomical units. 3. The Oort cloud. Much farther out, perhaps 2,000 to 100,000 astronomical units from the Sun, lies a theoretical spherical cloud of icy bodies, the reservoir of long-period comets. Objects in the inner Oort cloud might still orbit the Sun, making this a gravitational definition of the solar system's edge. Point 4. The heliosphere. This is the magnetic boundary, the region where the Sun's magnetic field and the solar wind dominate over the interstellar medium. This boundary, called the heliopause, lies somewhere between 120 and 140 AU and represents the edge we'll focus on, because this is where Voyager made its historic crossing and discovered the wall of fire. Understanding the heliosphere is crucial to appreciating what Voyager discovered. Imagine the Sun as the heart of a giant organism, constantly pumping out a stream of charged particles, mostly protons, and electrons at speeds of 300 to 800 kilometers per second, 186 to 497 miles per second. This outflow, called the solar wind, carries with it the Sun's magnetic field, creating an enormous magnetic bubble that extends far beyond the planets. This bubble, the heliosphere, inflates outward until it encounters resistance from the interstellar medium, the sparse gas, dust, and magnetic fields that fill the space between stars. The heliosphere has a complex structure with distinct regions. 1. The inner heliosphere, 0 to 80 astronomical units. This is where the solar wind flows freely outward at supersonic speeds. All the planets orbit within this region, bathed in the relatively steady stream of particles from the Sun. The solar wind here is hot, around 100,000 Kelvin, but incredibly sparse, about 5 to 10 particles per cubic centimeter at Earth's orbit, dropping to less than 0.01 particles per cubic centimeter by the time you reach the outer planets. 2. The termination shock 80100 AU. As the solar wind travels outward, it eventually encounters pressure from the interstellar medium at a distance of approximately 80 to 100 astronomical units. the solar wind suddenly slows from supersonic to subsonic speeds at transition, called the termination shock. It's like the shock wave that forms when a supersonic jet suddenly goes subsonic. Here, the solar wind begins to pile up, compressed and heated by the collision with interstellar matter. Voyager 1 crossed the termination shock in December 2004 at about 94 astronomical units. Voyager 2 crossed it in August 2007 at about 80 for astronomical units. The difference in crossing distances revealed something important. The heliosphere isn't perfectly spherical, it's asymmetric, compressed in some directions by the pressure of the local interstellar medium, and stretched in others. 3. The heliosheath 10120 AU. Beyond the termination shock lies the heliosheath, a turbulent, chaotic region where the solar wind is compressed and heated, swirling in complex patterns as it's diverted sideways before eventually flowing outward again. Think of it as a cosmic traffic jam, where the smooth flow of the solar wind becomes slow, hot, and turbulent. This region extends for 20 to 40 astronomical units, tens of billions of miles of roiling, compressed solar plasma. The Voyagers spent years traversing this region, measuring fluctuations in magnetic fields, detecting shock waves from solar storms that had taken years to reach this distance, and watching cosmic ray intensities gradually increase. For the heliopause 12010 AU. Finally, at the outer edge of the heliosheath, comes the heliopause, the true boundary where the outward pressure of the solar wind balances the inward pressure of the interstellar medium. This is where our solar system ends and interstellar space begins. The heliopause isn't a rigid wall, it's more like a dynamic membrane, expanding and contracting with the solar cycle and the sun's varying activity. When the sun is more active, producing stronger solar wind, the heliopause pushes farther out. During solar minimum, it contracts inward. It's also not a smooth sphere. The heliosphere is shaped more like a comet, with a rounded nose facing the direction of the sun's motion through the galaxy, and a long tail streaming behind. Recent research suggests it might even look more like a croissant or a deflated balloon. With lobes and asymmetries we're still working to understand. Let's follow Voyager's journey through these regions. After Neptune, both Voyagers continued outward, their velocity boosted by the gravitational assists from the giant planets. Voyager 1 was traveling faster, at approximately 17 kilometers per second, 38,000 miles per hour relative to the Sun. Voyager 2 followed at about 15 kilometers per second, 30,000 miles per hour. At these speeds, distance accumulates rapidly every day. Voyager 1 travels about 1.5 million kilometers every year. It covers more than 3.5 astronomical units farther than the distance between Earth and Mars. 1990s. Crossing the inner heliosphere throughout the 1990s, the Voyagers continued outward through the inner heliosphere. In 1990, Voyager 1 turned its camera back toward the inner solar system one last time, capturing the famous pale blue dot image of Earth from 6 billion kilometers away, the most distant photograph of Earth ever taken. After this, to conserve power, the cameras were permanently shut off. The spacecraft were now dedicated to particle and fields measurements, detecting the solar wind, cosmic rays, magnetic fields, and plasma waves. The 2000s, the termination shock as the millennium turned. Scientists began to see signs that Voyager 1 was approaching the termination shock. Instruments detected multiple crossings as the boundary fluctuated. Finally, in December 2004, at 94 astronomical units, Voyager 1 definitively crossed the termination shock and entered the heliosheath. Voyager 2 followed in August 2007 at 84 astronomical units, providing crucial comparative data that revealed the asymmetric nature of the heliosphere. The 2010s journey through the heliosheath. The journey through the heliosheath took years. During this time, both Voyagers measured increasing intensity of galactic cosmic rays penetrating from interstellar space, decreasing intensity of lower energy particles from the Sun complex, tangled magnetic field structures, evidence of magnetic reconnection events where field lines break and reconnect unexpectedly high temperatures. In the compressed solar wind, scientists watched anxiously. The heliopause was coming, but when exactly would the crossing occur? And what would the spacecraft detect when they passed through? Communication challenges grew increasingly severe. By the late 2000s, signals from Voyager 1 took more than 16 hours to reach Earth, traveling at the speed of light. Voyager 2 wasn't far behind. This meant that any command sent to the spacecraft required more than 32 hours. For a round-trip communication, send a command, wait 16 plus hours for it to arrive. Then wait another 16 plus hours for the spacecraft's acknowledgement. Moreover, the signal strength was diminishing. By the time Voyager's transmitter signal broadcasting at a mere 23 watts, about the power of a refrigerator light bulb, reached Earth after traveling billions of miles. It arrived with a power of only 10 to 16 watts, 20 billion times weaker than a digital watch battery. Receiving these whisper-faint signals required NASA's Deep Space Network 70-meter dish antennas located in California, Spain, and Australia, positioned strategically around the globe to maintain continuous contact as Earth rotates. Despite these challenges, communication remained intact. Data continued to flow back to Earth, a testament to the robust engineering of both the spacecraft and the ground systems. By 2012, all signs pointed to an imminent crossing. Cosmic ray counts were surging, solar particle counts were plummeting. Magnetic field measurements showed increasing strength and alignment. The heliopause was close, perhaps just months away. Scientists and engineers around the world watched the incoming data with bated breath. After 35 years of flight, after traveling 18 billion kilometers, after visiting the planets and their dozens of moons, after discovering volcanoes and geysers and rings and magnetic anomalies, after revolutionizing our understanding of the outer solar system, Voyager was about to make its most historic discovery. Yet, the crossing of the heliopause and the revelation of the wall of fire was about to begin. The year 2012 began like any other for the Voyager mission. Team analyzing data streams, monitoring spacecraft health, executing routine commands across the vast gulf of space. But as spring turned to summer, the data from Voyager 1 began showing something extraordinary. Something was changing. August 25, 2012. This is the date that would later be identified as the moment Voyager 1 crossed the heliopause and entered interstellar space, though at the time, no one was completely certain what was happening. Let's understand what Voyager 1 detected during this historic crossing, and why it took more than a year to confirm what had occurred. The three key signatures of the heliopause crossing. 1. The vanishing solar wind. Voyager 1's low-energy charged particle instrument detected a sudden, dramatic drop in the intensity of particles originating from the Sun. These solar particles, protons and electrons traveling at hundreds of kilometers per second, had been the dominant form of radiation throughout the entire mission. Beginning around August 25, 2012, the count rate of these particles plummeted to nearly zero. Within a few days, the solar wind had essentially vanished from Voyager 1's measurements. This was precisely what theories predicted should happen at the heliopause. Beyond this boundary, the solar wind no longer flows outward but instead deflects sideways, diverted by the pressure of the interstellar medium. 2. The surge in galactic cosmic ray. Simultaneously, Voyager 1's cosmic ray subsystem detected a sharp increase in galactic cosmic rays, high-energy particles originating from exploded stars, neutron stars, black holes, and other violent events throughout the Milky Way galaxy. These cosmic rays have been slowly increasing in intensity throughout Voyager's journey through the heliosheath. But at the heliopause crossing, their intensity suddenly jumped by about 9% and continued rising in the following weeks. Galactic cosmic rays are partially blocked by the heliosphere's magnetic fields and deflected by the solar wind. Once beyond the heliopause in true interstellar space, these rays would be encountered in their full, unshielded intensity, exactly what Voyager 1 was now detecting. 3. The magnetic field paradox. Here is where things got confusing. Scientists expected that crossing the heliopause would produce a dramatic change in the magnetic field direction. Inside the heliosphere, magnetic field lines originate from the Sun and generally point radially outward, though twisted and tangled. In interstellar space, the field should point in completely different directions, aligned with the galaxy's magnetic architecture rather than the Sun's. But Voyager 1's magnetometer showed something unexpected. The magnetic field strength increased slightly, but the field direction remained largely unchanged, still pointing in the same general direction as the Sun's magnetic field. This was puzzling. Had Voyager 1 truly crossed into interstellar space? Or was it in some intermediate region no one had predicted? The debate raged for more than a year. Mission scientists presented their findings at conferences, debated interpretations, and analyzed the data from every possible angle. Some argued Voyager 1 had crossed. Others insisted the spacecraft was still technically in a transition zone. Then came the breakthrough. In April 2013, a massive solar storm and eruption of plasma from the Sun finally reached Voyager 1's location, after propagating through space for more than a year. When this solar disturbance passed by, it caused the surrounding plasma to oscillate, generating plasma waves that Voyager's plasma wave instrument could detect. These plasma waves are like ripples on a pond. They travel at a speed determined by the density and composition of the surrounding plasma. By measuring the frequency of these oscillations, scientists could calculate the electron density of the plasma surrounding Voyager 1. The result was unambiguous. Voyager 1 was surrounded by plasma with a density of about 0.08 electrons per cubic centimeter, 40 times denser than the heliosheath plasma and perfectly consistent with the expected density of the local interstellar medium. There was no longer any doubt. On September 12, 2013, NASA officially announced Voyager 1 has left the solar system and entered interstellar space. The spacecraft had crossed the heliopause on August 25, 2012, at a distance of approximately 122 astronomical units from the Sun, about 18.2 billion kilometers, 11.3 billion miles, becoming the first human-made object to enter the space between the stars. Ed Stone, Voyager project scientist, described the moment. Voyager has entered a new region of space, a region never before visited by any spacecraft. We're in a truly alien environment, but the story was far from over. Voyager 2 was still on its way, and it carried something Voyager 1 lacked: a functioning plasma instrument, capable of directly measuring the solar wind particles. Fast forward to November 5, 2018. Voyager 2, traveling on a different trajectory at a slower speed, approached its own heliopause crossing. This time, the Voyager team was prepared. They knew what to look for. At approximately 119 astronomical units from the Sun, slightly closer than Voyager 1's crossing, Voyager 2 detected the same three key signatures: a sudden drop in solar wind particles, but this time measured directly by the still functioning plasma science experimenter; sharp increase in galactic cosmic rays; increase in magnetic field strength with surprisingly aligned field direction. What made Voyager 2's crossing scientifically invaluable was its working plasma instrument. The plasma science experiment, which had failed on Voyager 1 in 1980, was still operational on Voyager 2. This instrument could directly measure the speed, density, temperature, and pressure of the solar wind plasma, data that had to be inferred indirectly for Voyager 1. Here's what Voyager 2's plasma instrument revealed at the crossing. Solar wind speed dropped from about 400 kilometers per second to essentially zero within less than a day. Solar wind density plummeted from about 0.00 particles per cubic centimeter to unmeasurable level. Solar wind temperature and pressure collapsed. Simultaneously, plasma flow direction shifted, showing the solar wind deflecting parallel to the heliopause boundary, rather than flowing out. With these measurements provided the first direct, unambiguous observation of the solar wind terminating at the heliopause. It was the smoking gun that confirmed theoretical models of how the heliosphere works, but both crossings also revealed profound surprises, observations that challenged expectations and opened new mysteries. The magnetic field mystery. Both spacecraft detected that the magnetic field just inside and just outside the heliopause remained surprisingly aligned, roughly parallel to each other, despite the field lines originating from completely different sources. The Sun versus the galaxy closing parenthesis. This suggested a phenomenon called magnetic reconnection might be occurring at the heliopause field lines from the solar and interstellar magnetic fields breaking and reconnecting, allowing them to merge and align. This process would fundamentally change how particles and energy transfer across the boundary. The implications are profound. The heliopause might not be a simple barrier, but rather a dynamic interface where solar and interstellar magnetic fields interact, creating a complex transition zone. The narrow transition zone, scientists expected the heliopause to be a relatively thick boundary, perhaps stretching over several given the turbulent nature of plasma physics and the dynamic interplay between the solar wind and interstellar medium. Instead, both voyagers found the transition to be remarkably sharp, occurring over a distance of less than 1 astronomical unit, 150 million kilometers. In cosmic terms, this is razor-thin. The solar wind doesn't gradually fade away. It stops abruptly, like running into an invisible wall. The asymmetric heliosphere, the fact that Voyager 1 crossed at 122 astronomical units while Voyager 2 crossed at 119 astronomical units despite traveling in different directions revealed that the heliosphere is not a perfect sphere. The difference suggests the heliopause is compressed in the direction Voyager 2 traveled, toward the nose of the heliosphere, facing the direction of the Sun's motion through the galaxy and extended in the direction Voyager 1 traveled toward the sides. Think of it like the shape of a comet, rounded at the front, stretched at the sides and back. The local interstellar medium flows past our heliosphere like water flowing past a moving boat, compressing the front and stretching the tail. But the most shocking discovery was yet to come, a finding that would earn the nickname Wall of Fire, as both Voyagers crossed the heliopause and began measuring the temperature of the plasma in the heliosheath. And just beyond the boundary, they detected something extraordinary. The temperature was far higher than anyone predicted. Models and earlier observations suggested the local interstellar medium should have a temperature of about 15,000 to 30,000 Kelvin, already extremely hot by terrestrial standards, but consistent with theoretical predictions. Instead, both Voyagers measured temperatures of 30,000 to 50,000 Kelvin, 0 to 90,000 degrees Fahrenheit, in the region just inside and just outside the heliopause. This wasn't just slightly warmer than expected. It was nearly twice as hot as predicted, hot enough to be compared to the surface of many stars. The heliopause wasn't just a magnetic boundary. It was a thermal boundary, a collision zone where the solar wind and interstellar medium smashed together, compressing and heating to extraordinary temperatures. Scientists began calling it the Wall of Fire, a dramatic name for a dramatic discovery. But here's the paradox that makes this discovery even more extraordinary. Despite these extreme temperatures, the spacecraft themselves experienced no danger whatsoever. Why? Because temperature and heat are not the same thing. Let's explore this mind-bending physics in our next section, where we dive deep into the Wall of Fire, understand why it exists, and unravel the beautiful paradox of a region simultaneously scorching hot and harmlessly empty. Imagine standing at the edge of a cosmic furnace, a boundary where plasma reaches temperatures of 30,000 to 50,000 Kelvin, nearly 10 times hotter than the surface of the Sun, which only reaches about 5,800 Kelvin. Closing parenthesis. Now imagine walking through this inferno completely unscathed, not even feeling a hint of warmth. This is the paradox of the Wall of Fire at the heliopause, a region simultaneously hotter than any environment on Earth, yet so sparse that even a spacecraft built in the 1970s could pass through without damage. Let's unravel this extraordinary discovery piece by piece. The shocking temperature readings. When Voyager 2's plasma science experiment measured the electron temperature in the heliosheath, and at the heliopause crossing in 2018, the data revealed plasma temperatures of approximately 30,000 to 50,000 Kelvin. To put this in perspective, the surface of the Sun, approximately 5,800 Sun's corona outer atmosphere, 1 to 2 million core of the Sun, approximately 15 million. Heliopause wall of fire, 30,000 to 50,000. Room temperature on Earth, approximately to 193 K68F Voyager 1, using indirect measurements from plasma oscillations detected in 2013. Confirmed similar temperatures in its region of the heliopause. This was stunning. Theoretical models had predicted the very local interstellar medium VLISN should have temperatures of 15,000 to 30,000 K, already extremely hot, but less than half of what was actually measured. Why is this called a wall of fire? The term isn't official NASA nomenclature, it's a colloquial name that emerged in scientific discussions and popular science coverage. And while it's somewhat dramatic, it's not entirely metaphorical. The heliopause truly is a wall in the sense that it's a sharply defined boundary, where conditions change abruptly. And it's truly fire in the sense that the plasma there reaches temperatures far exceeding any terrestrial fire on Earth typically reaches. Wood fire, approximately 600–800 Celsius, approximately 900 to 1100 K. House fire, approximately 1000 Celsius, 1300 K. Propane torch, approximately 1980 Celsius, approximately 2000 to 150 K. The heliopause is more than 10 times hotter than even the most intense chemical fires, comparable instead to the plasma inside a fusion reactor or the surface of certain stars. Where exactly is this region located? The wall of fire exists primarily in two adjacent regions: the outer heliosheath, the compressed, turbulent region immediately inside the heliopause, where the solar wind has been slowed, compressed, and heated by its impending collision with the interstellar medium, the heliopause boundary itself, the sharp transition zone where the solar wind and interstellar medium meet and interact, the inner VLISN, the region immediately outside the heliopause, where interstellar plasma is compressed and heated by the pressure of the heliosphere, pushing against it. Both Voyagers detected elevated temperatures in all three regions, with peak temperatures occurring right at the boundary and in the compressed plasma on both sides. The wall extends roughly parallel to the heliopause boundary, wrapping around the entire heliosphere like a glowing shell. It's not uniform in thickness, or temperature measurements suggest it might be only 0.1 to 0.5 astronomical units thick in some places, but its high temperature extends throughout the compression zone where the two plasmas interact. How both Voyagers independently confirmed it: the fact that both spacecraft, traveling along different paths and crossing the heliopause at different locations and times, measured similar elevated temperatures, provides strong confirmation that this is a real, persistent feature of the heliopause, not a temporary anomaly or measurement error. Voyager 1 crossed in 2012 during a different phase of the solar cycle than Voyager 2's 2018 crossing, yet both detected the hot plasma. This indicates the wall of fire is a stable structural feature of the heliosphere interstellar boundary, not dependent on short-term variations in solar activity. The physics behind the heat. Now we come to the crucial question: why is it so hot? The answer lies in one of the most fundamental processes in astrophysics: compression heating. Think about what happens at the heliopause. On one side, you have the solar wind, a supersonic stream of plasma flowing outward from the Sun at 300 to 800 kilometers per second, carrying magnetic fields, energy, and momentum. On the other side, you have the local interstellar medium, a sparse gas of atoms, ions and electrons, plus dust grains and cosmic rays, with its own magnetic field and pressure. Neither side is willing to give way easily. The solar wind pushes outward. The interstellar medium pushes back. The result is a collision zone where both plasmas compress against each other. Here's the physics: when a gas or plasma is compressed, its temperature rises. This is thermodynamics 101, embodied in the ideal gas law: PV equals nRT, where P is pressure, V is volume, N is the number of particles, R is the gas constant, and T is temperature. If you compress a gas, decrease V while the number of particles N remains constant, either the pressure P or temperature T must increase, usually both. At the heliopause, plasma from both the solar wind and the interstellar medium is compressed into a narrow boundary region. This compression increases both the plasma density and temperature. Additionally, kinetic energy converts to thermal energy. The solar wind particles are moving at hundreds of kilometers per second. When they reach the termination shock and then the heliopause, they suddenly slow down or stop. Where does all that kinetic energy go? It converts into heat-random thermal motion of the particles. Instead of all moving together in one direction at high speed, the particles now move randomly in all directions at even higher individual speeds, which we measure as increased temperature. Furthermore, magnetic reconnection releases additional energy when magnetic field lines from the solar and interstellar fields interact at the heliopause. They can break and reconnect in new configurations. This magnetic reconnection process releases stored magnetic energy as heat and kinetic energy, further heating the plasma. Think of magnetic field lines like rubber bands stretched tight. When they break and reconnect, they snap, releasing energy just like releasing a stretched rubber band. At the heliopause, this happens continuously on enormous scales, pumping energy into the plasma. The result: a narrow band of superheated plasma wrapping around the entire heliosphere, the wall of fire. Why the spacecraft don't melt? Understanding particle density, here comes the beautiful paradox that makes this discovery so mind-bending. Despite temperatures of 30,000 to 50,000 K, the Voyager spacecraft experienced absolutely no heating effects. As they passed through the heliopause, the spacecraft's internal temperature remained steady, regulated by its radioisotope thermoelectric generators and thermal control systems, just as it had been for decades. How is this possible? The answer lies in understanding the difference between temperature and heat. Temperature measures the average kinetic energy of individual particles, how fast they're moving. At 50,000 K, each particle atom, ion, or electron is zipping around at tremendous speed, tens, 200s of kilometers per second for ions, thousands of kilometers per second for electrons. Heat measures the total thermal energy temperature multiplied by the number of particles and their heat capacity. At the heliopause, the particle density is extraordinarily low in the outer heliosheath, approximately 0.02 particles per cubic centimeter in the VLISM, just outside the heliopause, approximately 0.05 to 0.1 particles per cubic centimeter. To put this in perspective, Earth's atmosphere at sea level, approximately 2.5 times 1019 particles per cubic centimeter, a laboratory high. Vacuum, approximately key particles per cubic centimeter. The heliopause, approximately 0.05 particles per cubic centimeter. The heliopause plasma is more than a trillion times less dense than Earth's atmosphere, even though each individual particle is moving incredibly fast. High temperature. There are so few particles that they collectively carry very little thermal energy. When a high-speed particle from this hot plasma hits the Voyager spacecraft, it does deposit a tiny amount of energy, but collisions are so rare, only a few particles hitting any given square centimeter of the spacecraft per second, that the total energy transfer is negligible. It's like the difference between standing in a rainstorm, many cool droplets, equals you get wet and cold being hit by an occasional drop. From a fire hose, each drop has more energy, but there are so few that you barely notice, or even better, imagine bullets flying past you at supersonic speed, but so far apart that only one might graze you per day. Each bullet has tremendous kinetic energy, but because you're hit so rarely, the total energy transfer is trivial. The same principle explains why spacewalkers don't burn up in Earth's thermosphere. Earth's thermosphere, at an altitude of 200 to 500 kilometers where the International Space Station orbits, has temperatures of 500 to 2,500 K hotter than molten lava. Yet astronauts on spacewalks don't spontaneously combust. Why? Same reason. The particle density at ISS altitude is only about 1010 to kc particles per cubic centimeter of vacuum by Earth's surface standards. The few particles that do hit the spacesuit are hot, but there are so few of them that they transfer negligible heat. The heliopause is even more extreme, far hotter, but also far more sparse. Plasma wave instrument revelations. One of the most important tools for understanding the wall of fire has been Voyager's Plasma Wave Subsystem PWS, an instrument designed to detect oscillations and waves in the surrounding plasma. How the instrument works. The PWS consists of two long antennas, each 10 meters long, extending from the spacecraft like whiskers. These antennas detect electric fields associated with plasma, waves, oscillations in the electron density and temperature that propagate through space like ripples on a pond when a disturbance passes through plasma, such as a shock wave from a solar storm or a magnetic reconnection event. It causes the electrons to oscillate at a frequency determined by the plasma's electron density. This frequency is called the plasma frequency. By measuring the frequency of these oscillations, scientists can calculate the electron density of the surrounding plasma using the formula F_P equals 8,980 times square root N_E, where F_P is the plasma frequency in Hz, and N_E is the electron density in electrons per cubic centimeter. Density measurements of the interstellar medium using the PWS. Voyager 1 detected plasma oscillations in 2013 that revealed an electron density of about 0.08 electrons per cubic centimeter in the local interstellar medium, significantly higher than the approximately 0.002 per cubic centimeter in the heliosheath. This confirmed Voyager 1 had entered a fundamentally different region of space with different plasma properties. Voyager 2's PWS detected similar oscillations during and after its heliopause crossing, providing independent confirmation of the elevated density in interstellar space. Unexpected findings. Higher density than predicted. Interestingly, the measured electron density of approximately 0.05 to 0.1 per cubic centimeter in the VLISM was higher than some earlier models predicted. Previous estimates, based on observations of nearby stars and interstellar absorption lines, suggested densities might be closer to 0.02 to 0.05 per cubic centimeter. The higher measured density has important implications. It means the local interstellar medium exerts more pressure on the heliosphere than expected, which could explain why the heliosphere is more compressed than older models suggested. It also affects estimates of how much galactic cosmic radiation is filtered by the heliospheric boundary, and how the heliosphere's shape and size change with the solar cycle. Persistent plasma waves in interstellar space. 2021 discovery. In one of the most remarkable recent findings, scientists analyzing Voyager 1 data discovered something unexpected: continuous, faint plasma oscillations occurring in the local interstellar medium. These weren't just occasional oscillations triggered by solar storm shock waves reaching Voyager's location. Instead, starting in 2017, Voyager 1's PWS began detecting a weak but persistent hum, a nearly continuous plasma frequency signal, corresponding to electron densities around 0.13 per cubic centimeter. This discovery, published in 2021 by Stella Ocker and colleagues, revealed that interstellar space isn't silent and static. Instead, there appears to be a continuous, gentle humming of plasma oscillations, possibly caused by turbulence in the interstellar medium or interactions with low-energy cosmic rays. This has profound implications. It means we can now map the density structure of the local interstellar medium in real time as Voyager travels through it, rather than waiting for rare solar storm shock waves to illuminate the plasma. The density has varied slightly as Voyager moves from about 0.08 to 0.13 electrons per cubic centimeter between 2013 and 2023, indicating the interstellar medium has structure and isn't perfectly uniform. Magnetic field mysteries. While the temperature and density measurements at the heliopause provided thrilling discoveries, the magnetic field observations raised equally profound puzzles. Expected, turbulent, twisted field lines models predicted that at the heliopause, the solar and interstellar magnetic fields would be oriented in completely different directions. The solar magnetic field originates from the Sun's dipole and is carried outward, and twisted by the solar wind into a complex spiral pattern. The interstellar magnetic field, by contrast, is aligned with the large-scale structure of the Milky Way galaxy, oriented roughly parallel to the galactic plane, shaped by the galaxy's rotation and the pressure of cosmic rays and interstellar gas. When these two fields meet, scientists expected dramatic shearing and reconnection, field lines breaking, twisting and reconnecting in chaotic patterns, creating a turbulent magnetic boundary layer. Reality, more aligned than anticipated instead. Both voyagers found that the magnetic field direction changed relatively little. As they crossed the heliopause, the field strength increased by about 50%, from approximately 0.3 to approximately 0.5 nanotsla, but the field direction remained surprisingly aligned, pointing in roughly similar directions. On both sides of the boundary, this suggests the solar and interstellar magnetic fields are more aligned than pure chance would predict, as if they've somehow organized themselves to be parallel at the boundary. Implications for magnetic reconnection. The unexpected field alignment has major implications for understanding how magnetic reconnection occurs at the heliopause. Magnetic reconnection happens most efficiently when field lines are anti-parallel, pointing in opposite directions. If the fields are already aligned, reconnection should be less frequent and less energetic. Yet the high temperatures and plasma heating at the heliopause require significant energy input, and magnetic reconnection is one of the most efficient ways to convert magnetic energy into heat. This creates a puzzle. How do you get efficient heating without strongly misaligned fields? One possible explanation is magnetic draping. As the interstellar magnetic field encounters the heliosphere, which is moving through space at about 26 kilometers per second, the field lines might drape around the heliosphere, like water flowing around a rock in a stream. This draping process could cause the interstellar field to become more aligned with the solar field at the heliopause, while still allowing localized reconnection events to occur. How magnetic fields connect across the boundary. Recent theoretical work suggests the heliopause might be magnetically porous, allowing some field lines to connect across the boundary, creating a complex topology where some field lines are purely solar, some purely interstellar, and some connected across the boundary. This would allow particles to cross the boundary more easily than a completely closed magnetic barrier would permit, which could explain why the cosmic ray transition at the heliopause, while dramatic, isn't an absolute cutoff. It might also create channels for energy transfer across the boundary, contributing to the observed heating. The wall of fire is not what anyone expected, and that's what makes it scientifically revolutionary. It revealed temperatures far higher than models predicted, a sharper boundary transition than expected, unexpected magnetic field Allen-Menthager, interstellar plasma density than some estimators, Scontian plasma oscillations in interstellar space, a dynamic, energy-rich boundary rather than a passive membrane. And most importantly, it transformed the heliopause from an abstract theoretical concept into a tangible, measurable, physically extreme environment that we can now study with real data from real spacecraft. The wall of fire is the frontier, the place where our solar home ends and the vast galactic wilderness begins. But what does this discovery actually mean for us? Why should anyone beyond the scientific community care about temperature readings from 120 astronomical units away? In our next section, we'll explore the profound implications of the wall of fire discovery for our understanding of the solar system, for the protection of life on Earth, and for the future of human space exploration. Every discovery in science has two dimensions: what we learn about the universe and what we learn about ourselves. The wall of fire at the heliopause is no exception. This isn't just an abstract finding about plasma physics in distant space. It's a revelation about the protective bubble within which all human history has unfolded, and what threats might await us if that protection ever failed. Let's explore what the heliopause discoveries mean, starting with the most fundamental question redefining the solar system's edge for centuries. Humans defined the solar system by what we could see, the planets. First just the naked-eye planets Mercury through Saturn, then Uranus and Neptune with telescopes, and eventually smaller bodies like asteroids, comets and dwarf planets. But Voyager's discoveries have forced a paradigm shift. The solar system's true edge isn't a planet or even a distant Kuiper belt object. It's a magnetic boundary, a dynamic, living structure created by the sun's breath. This changes everything about how we think of our cosmic neighborhood. We now understand the solar system not as a collection of objects orbiting the sun, but as a unified magnetic environment, a bubble of solar origin plasma and fields, distinct from the interstellar medium with a well-defined if shifting boundary. Every planet, moon, asteroid and comet we've ever observed orbits deep within this bubble, protected by it, shaped by it, and fundamentally connected to it. It's not a distant planet, it's a magnetic boundary. This magnetic definition has practical importance when we ask questions like how large is the solar system, or where does our sun's influence end? The answer isn't at Neptune's orbit, or at the Kuiper belt, or at the Oort cloud. The answer is at the heliopause, approximately 1 to 0140. O from the sun, where the solar wind and magnetic field can no longer push outward against the interstellar medium. This is where solar physics ends and interstellar physics begins. The heliosphere is a dynamic, living structure, one of the most important revelations from Voyager's continued observations is that the heliosphere isn't static, it's constantly changing, breathing like a living organism. How it changes with the solar cycle. The sun's activity follows an approximately 11-year cycle, varying between solar minimum, fewer sunspots, weaker solar wind, and solar maximum, more sunspots, stronger solar wind, more frequent solar storms. During solar maximum, the enhanced solar wind pressure pushes the heliopause farther outward. Estimates suggest it might expand by 10 to 30 during peak solar activity. During solar minimum, reduced solar wind pressure allows the interstellar medium to compress the heliosphere inward. This means the heliopause is constantly moving in and out, like a slowly pulsing balloon. Voyager may have detected evidence of this, small variations in plasma density and temperature measured over several years suggest the heliopause boundary passed back and forth over the spacecraft multiple times after the initial crossing, like standing at the tide line as waves wash in and out. Long-term variations and evolution. On even longer time scales, the heliosphere's size and shape vary with the sun's passage through different regions of the galaxy. Our solar system is currently located in the local interstellar cloud, also called the local fluff, a small region of slightly higher density interstellar gas, probably the remnants of ancient supernova explosions. As the sun travels through the galaxy at about 26 kilometers per second, we're currently exiting the local interstellar cloud and may enter a different region of interstellar space within the next few thousand years. If we enter a region with higher interstellar density and pressure, the heliosphere could compress significantly, perhaps shrinking to only 50 to 80 astronomical units. If we enter a less dense region, it might expand to 200 astronomical units or more. These changes would have measurable effects throughout the solar system, potentially affecting cosmic ray flux, reaching the inner planet's trajectories of incoming comets from the Oort cloud, density of neutral interstellar atoms flowing into the solar system, even, possibly, Earth's climate, though this remains highly speculative, our cosmic shield. Perhaps the most profound implication of the heliopause discovery is understanding it as humanity's shield against the harsh radiation environment of interstellar space. Protection from galactic cosmic radiation, galactic cosmic rays, GCs, are high-energy particles, mostly protons, but also heavier atomic nuclei accelerated to near light speed by supernova explosions, pulsars, and other violent cosmic events. They fill the galaxy, traveling through interstellar space and bombarding everything they encounter. These cosmic rays are dangerous. They can penetrate deep into biological tissue, damaging DNA and increasing cancer risk. They can disrupt electronic systems, causing computer errors and memory corruption. They can generate secondary radiation showers when they hit matter. They represent one of the most significant radiation hazards for long duration space mission. The heliopause filters dangerous particles. The heliosphere acts as a partial shield against GCs through several mechanisms. Magnetic deflection. Charged cosmic ray particles are deflected by magnetic fields as they encounter the tangled, compressed magnetic fields at the heliopause and in the heliosheath. Many lower energy cosmic rays are deflected away or scattered, preventing them from reaching the inner solar system. Solar wind pressure, the outward flowing. Solar wind creates an outward pressure that opposes the inward motion of cosmic rays, making it harder for them to penetrate deep into the heliosphere. Energy loss as cosmic rays pass through the heliosheath and heliopause regions. They interact with plasma and magnetic fields, losing energy through various processes. This reduces the intensity and average energy of cosmic rays that reach the inner planets. The radiation environment inside versus outside. Voyager's measurements have quantified this shielding effect. Inside the heliosphere at Earth's orbit, galactic cosmic ray flux is about 30 to 50% lower during solar maximum and 10 to 20% lower during solar minimum compared to interstellar space. The difference is most pronounced for lower energy cosmic rays below approximately 1 GeV per nucleon, which are more easily deflected by magnetic fields. Higher energy cosmic rays above approximately 10 GeV per nucleon are less affected and penetrate the heliosphere more readily. Intensity increase. Voyager's measurements when Voyager 1 crossed the heliopause in 2012. Its cosmic ray subsystem detected an immediate 9% increase in galactic cosmic ray intensity, which continued to rise to approximately 25 to 30% higher than heliosheath levels within a year. Voyager 2 confirmed similar increases when it crossed in 2018. This means interstellar space is significantly more radiation intense than even the outer regions of our solar system. For context, an astronaut traveling in interstellar space would receive a radiation dose roughly 30 to 50% higher than an astronaut at the same distance inside the heliosphere, and both would already be receiving dangerous radiation doses without heavy shielding. What happens if the heliosphere shrinks? This raises a concerning question. What if the Sun's activity declines significantly? Or what if our solar system enters a denser region of interstellar space that compresses the heliosphere inward? If the heliopause moved closer to the Sun, say, shrinking from 120 astronomical units to 80 astronomical units, or even less, the radiation environment throughout the solar system would change. Increased cosmic ray flux at Earth's orbit, possibly by 10 to 30%, could increase radiation exposure for astronauts and satellite changes in atmospheric chemistry from cosmic ray interactions with upper atmosphere molecules. Potential climate effects highly speculative. If cosmic rays significantly influence cloud formation, as some controversial theories suggest, increased radiation for future Mars and Moon bases, which have no magnetic fields, for additional protection implications for space exploration. The heliopause discoveries aren't just abstract astrophysics, they have direct, practical implications for human space exploration. Astronaut safety on Moon and Mars missions. Both the Moon and Mars lack global magnetic fields. Mars lost its magnetic field billions of years ago. The Moon never had a strong one. This means they have no intrinsic protection against cosmic radiation beyond the heliosphere's shielding. On Earth, we're protected by 3 layers. The heliosphere blocks some cosmic rays. Earth's magnetic field deflects charged particles. Earth's atmosphere absorbs radiation. That makes it through the first 2 layers. On the Moon or Mars surface, astronauts would have only the heliospheric shielding, and Mars's thin atmosphere provides minimal additional protection. Radiation exposure calculations. NASA's calculations suggest that astronauts on a Mars mission would receive radiation doses of approximately 0.3 to 0.6 millisieverts per day on the Martian surface, from galactic cosmic rays. Total mission dose of 500 1 to 100 millisieverts for a round-trip mission with surface stasis. exceeds NASA's current career radiation limits for astronauts and significantly increases cancer risk. Understanding the heliosphere's shielding effectiveness and how it varies with solar cycle and interstellar environment is crucial for accurately calculating these risks and designing appropriate countermeasures, shielding requirements for deep space travel for missions beyond Mars to the asteroid belt, Jupiter system, or even future interstellar precursor missions. Understanding the radiation environment becomes even more critical. Voyager's data helps engineers design radiation shielding by providing accurate measurements of the energy spectrum of cosmic rays in different regions. Show radiation intensity changes with solar cycle effectiveness of the heliosphere's natural shielding. This data informs designs for water-filled radiation shelters aboard spacecraft. Magnetic shielding concepts using artificial magnetic fields, timing of missions to coincide with solar maximum when cosmic ray flux is lower. Safe haven architectures for Moon and Mars bases with thick regolith shielding. Real-world applications for mission planning. NASA's IMAP mission Interstellar Mapping and Acceleration Probe, which launched in September 2025 and reached its operational orbit in January 2026, is now providing real-time monitoring of the heliosphere's changing structure from its vantage point at the Sun-Earth L1 Lagrange point. IMAP will map how the heliosphere boundary changes over the solar cycle, track cosmic ray variations, and provide early warning of space weather events. All critical data for planning future deep space missions. Additionally, NASA is studying concepts for an interstellar probe, a next-generation spacecraft that would reach the heliopause in just 15 to 20 years compared to Voyager's 35 to 40 years using advanced propulsion and trajectory planning. This mission would carry modern instruments to study the heliopause structure in far greater detail than Voyager's 1970s technology allows. The Sun's journey through the galaxy. Finally, let's zoom out to the largest scale. The heliosphere discoveries reveal our solar system's relationship with the broader galaxy and how that relationship has changed over time and will change in the future. Our solar system is moving through space. The Sun isn't stationary. It orbits the center of the Milky Way galaxy at a speed of approximately 120 kilometers per second, completing one full orbit about every 125 to 250 million years, sometimes called a galactic year. But superimposed on this orbital motion, the Sun also moves at about 26 kilometers per second relative to the local standard of rest, the average motion of nearby stars. This means we're cruising through the local interstellar medium like a boat moving through water, creating the bow shock or compressed region at the front of our heliosphere. Encountering different interstellar environments as we move, we pass through regions of varying interstellar density, temperature, and composition. The local interstellar cloud. Right now, our solar system is located in or near the edge of the local interstellar cloud, a small, relatively warm, low-density region about 30 light-years across. This cloud is probably a remnant of supernova explosions that occurred millions of years ago, now cooled and dispersed but still distinguishable from the surrounding medium. The local interstellar cloud has temperature approximately 6,000 to 7,000 K, relatively warm density approximately 0.3 atoms per cubic centimeter, relatively low partially ionized hydrogen and helium. What happens when we enter denser regions? Astronomical observations and computer models suggest that within the next 10,000 to 50,000 years, our solar system will likely exit the local interstellar cloud and enter a different region, possibly the G cloud or other nearby interstellar structures. If we enter a denser cloud, say 1 to 3 atoms per cubic centimeter instead of 0.3, the increased pressure would compress the heliosphere significantly. The heliopause might move inward to 50 to 80 astronomical units closer than the Kuiper belt's inner edge. This would have dramatic effects: increased cosmic ray flux throughout the solar system, including at Earth more neutral interstellar atoms flowing into the inner solar system, potential climate effects on Earth, highly speculative changes to the structure of the heliosheath and termination shock, historical variations in cosmic radiation, Some scientists have proposed that variations in the heliosphere's size, due to changing interstellar environments, could explain some mysteries in Earth's geological record. Periodic climate shifts coinciding with the Sun's passage through spiral arms, which have higher interstellar density variations in isotope ratios in ice cores, and sediment records extinction events possibly correlated with increased cosmic radiation during periods of compressed heliosphere. Will this affect Earth's climate or biology? This remains highly controversial and speculative, but some researchers have explored potential connections. The cosmic ray climate hypothesis. Some scientists have proposed that galactic cosmic rays might influence Earth's climate by affecting cloud formation. The theory suggests that cosmic rays create ionization in the atmosphere, which could see cloud formation, potentially cooling the planet. If true, variations in heliospheric shielding, and thus cosmic ray flux, could modulate cloud cover and temperature over geological timescales. However, this hypothesis remains unproven and contested. Most climate scientists consider the effect, if real, to be minor compared to other climate drivers like greenhouse gases, solar luminosity variations, and orbital changes. Biological effects. In principle, increased cosmic radiation during periods of compressed heliosphere could increase mutation rates and radiation stress on organisms, potentially influencing evolution over million-year timescales. But quantifying this effect is extremely difficult, and it's unclear whether it would be significant compared to other evolutionary pressures. The big picture, the wall of fire, and heliopause discoveries have transformed our understanding from the solar system ends where the planets end to a far richer, more nuanced picture. We live inside a protective magnetic bubble created by our Sun. This bubble has a sharp, hot boundary at the heliopause. The wall of fire, the boundary, is dynamic, expanding and contracting with solar activity. The heliosphere shields us from dangerous galactic radiation. Our solar system is moving through changing interstellar environments. Understanding this boundary is critical for future space exploration. We, in the most literal sense, children of the Sun, not just because sunlight powers life on Earth, but because the Sun's magnetic embrace shields us from a universe that would otherwise be hostile to life as we know it. And we're only now beginning to understand this cosmic shield, thanks to the tiny spacecraft built nearly 5 decades ago. Speaking of those spacecraft, where are they now? And how much longer will they continue this extraordinary mission? Let's find out. As I'm speaking to you today in 2026, both Voyager spacecraft continue to hurtle outward through interstellar space, lonely ambassadors from Earth, traveling farther from home with each passing second. Where are they now? 2026 update. Voyager 1, the farther and faster of the twin spacecraft, is currently more than 8 billion miles, 25.4 billion kilometers, or 170 astronomical units from Earth. To put this in perspective, light takes over 23 hours to travel from Earth to Voyager 1. It's more than 130 times farther from the Sun than Earth is if you could drive to Voyager 1 at highway speed 70 miles per hour. It would take 25,000 years to reach it. And here's the historic milestone approaching. In November 2026, just months from now, Voyager 1 will become the first human-made object to reach 1 light day from Earth. This means that any command we send will take exactly 24 hours to reach the spacecraft, traveling at the speed of light, and then we must wait another 24 hours for Voyager's response. A simple hello and hello back takes 48 hours. Think about that. A 2-word conversation spanning to full days, across a void so vast it challenges human comprehension. Voyager 2 follows behind at approximately 13.2 billion miles, 21.2 billion kilometers, or 141.5 astronomical units from Earth. Communication time with Voyager 2 is currently about 19.5 hours one way. Current speed and trajectory. Voyager 1 is traveling at approximately 17 kilometers per second, 38,000 miles per hour. Relative to the Sun, heading in the direction of the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445. Voyager 2 is traveling at approximately 15 kilometers per second, 30,000 miles per hour, heading toward the constellation Telescopium and the star Ross 148, which it will pass in about 40,000 years. Both spacecraft are traveling fast enough to escape the solar system permanently. They will never return, never be slowed by the sun's gravity, never come home. What they're measuring right now, despite being nearly 49 years into their missions, both Voyagers continue to return valuable scientific data. Currently active instruments include, on Voyager 1, Cosmic Ray Subsystem, measuring galactic cosmic rays low-energy charged particle instrument, detecting low-energy particles magnetometer, measuring magnetic field strength and direction plasma, Wave Subsystem detecting plasma oscillations and density on Voyager 2, has one more working instrument than Voyager 1. Cosmic Ray Subsystem Low-Energy Charged Particle Instrument Magnetometer, Wave Subsystem Plasma Science Experiment still functioning. Unlike Voyager 1's, the spacecraft are currently measuring density variations in the local interstellar medium magnetic field structure of interstellar space galactic cosmic ray flux and energy spectrum plasma wave activity and turbulence possible interactions between the heliosphere's tail region and interstellar medium. This real-time data from interstellar space is irreplaceable. No other human-made object is currently in this environment. Power management and mission end. The Voyager's greatest limitation is also their greatest achievement. The radioisotope thermoelectric generators that have powered them for nearly 50 years are gradually running out. Our TG power decline, losing about 4 watts per year. Plutonium-238 has a half-life of 87 years, which means every 87.7 years, half of the plutonium atoms decay, reducing heat output by half. But even before accounting for radioactive decay, the thermocouples that convert heat to electricity gradually degrade over time, reducing efficiency. The combined effect is a power loss of approximately 4 watts per year, roughly 0.8% of remaining power annually. At launch in 1977, each Voyager's RTGs produced about 470 watts. In 2026, they produce approximately 240 watts, just over half their original output. By 2030, power will drop to about 220 watts. Instrument shutdowns to conserve power. To keep the mission alive as long as possible, NASA engineers have been strategically shutting down instruments and non-essential systems, prioritizing those that provide the most valuable interstellar science. Recent shutdowns include October 2024. Voyager 2's plasma science experiment heating element turned off, though the instrument continues operating at reduced effectiveness. January 2025. Voyager 1's low-energy charged particle instruments B detector shut down scheduled for 2026. Voyager 1's cosmic ray subsystem will be shut down later this year. Each shutdown buys a few more years of operation for the remaining instruments. Expected end dates late 2020s to early 2030s, based on current power projections and shutdown plans. Engineers estimate Voyager 2 will likely operate at least one science instrument until approximately 2028 to 2030. Voyager 1 might continue with at least one instrument until 2030 to 2032 after the last science instrument shuts down. There may be a brief period, perhaps a few years, when the spacecraft retains enough power to maintain attitude control and transmit engineering data information about the spacecraft's health and status, even without scientific instruments. Final communications. What will be the last message eventually, probably in the mid-2030s? The power level will drop below the threshold needed to operate the transmitter and attitude control system. At that point, the spacecraft will lose the ability to point its antenna toward Earth, stop transmitting signals, go silent. Last message from each Voyager will likely be a simple engineering status report: temperature readings, power levels, system status transmitted automatically, received by the Deep Space Network 23+ hours later and stored in NASA's archives. There will be no dramatic farewell speech, no final photograph, no last words. just the cessation of signal one day's expected transmission that never arrives, and then silence. But even after communications end, the spacecraft will continue. With no atmosphere to slow them, no obstacles to collide with, they will drift outward through the galaxy for hundreds of millions of years, carrying their golden records humanity's message to the stars long after human civilization has transformed, beyond recognition, or perhaps ceased to exist entirely. The data they're still sending, despite the limitations. The scientific value of Voyager's ongoing measurements cannot be overstated. Active instruments as of 2026, the instruments still operating. For on Voyager 1, 5 on Voyager to continue to return data that no other mission can provide. Scientific value of continued measurements, every day of continued operation, adds to an irreplaceable dataset mapping the interstellar medium as Voyager travels. It's creating the first direct measurement of how interstellar plasma density, temperature, and magnetic field vary with location. This is like drawing the first maps of an unknown continent. Long-term monitoring, watching how conditions change over years and decades, reveals processes we couldn't see with short-term observations. Seasonal variations in the heliospheres, structure, the effects of solar cycles on the heliopause, long-term trends in cosmic ray flux. Unexpected discoveries, some of Voyager's most important findings, came years or decades into the mission, long after the primary objectives were complete. Who knows what surprises await in the next few years of data? The case for a new interstellar mission. Voyager's success has inspired proposals for a new generation of interstellar exploration. Voyager's 1970s technology versus modern capabilities. Voyager was built with technology from the mid-1970s. Computer memory, 69 kilobytes, less than a basic smartphone. Photo computer processing, 8,000 instructions per second, millions of times slower than a smartphone. Data transmission rate, 160 bits per second slower than 1970s telephone modems. Camera resolution, 640 for 180 pixels, worse than a basic webcam. Imagine what we could learn with modern technology. High-definition cameras and spectrometers, plasma and particle detectors, real-time spectroscopy, and composition analysis. Speed data transmission, AI-based autonomous decision-making. Proposed missions. Interstellar probe concept. NASA's interstellar probe concept would be specifically designed to study the heliosphere and local interstellar medium with modern instrumentation. Key features: speed, using advanced trajectories, possibly including solar orbit maneuvers or solar sails, could reach the heliopause in just 15 to 20 years instead of Voyager's 35 to 40 years instruments. Modern plasma detectors, magnetometers, particle telescopes, energetic neutral atom imagers, and possibly even optical cameras to image the heliosphere from outside a mission profile. Not just pass through the heliopause once, but potentially loiter in that region, measuring its structure in detail. Power, advanced RTGs, or possibly solar electric propulsion in the inner solar system. Target launch dates and objectives. Current planning suggests a launch in the late 2030s or early 2040s would be possible, with heliopause arrival in the 2050s, 2060s. NASA's IMAP mission launched 2026. While not an interstellar mission, NASA's Interstellar Mapping and Acceleration Probe IMAP, which launched in September 2025 and reached operational orbit in January 2026, is already providing crucial complementary data. IMAP orbits the Sun-Earth L1 point, mapping the heliosphere from inside, measuring energetic neutral atoms created at the heliopause low wind conditions throughout the solar cycle. Cosmic ray variations as they enter the heliospheritica IMAP, and the still operating Voyagers provide an unprecedented inside and outside view of the heliosphere. Measurements from Earth's orbit combined with direct sampling from interstellar space. Asterisk: the Voyager era is entering its final chapter. Within a decade, both spacecraft will likely fall silent, their plutonium hearts finally too weak to maintain contact with the civilization that built them. But the data they've sent back, the discoveries they've made, will echo through human knowledge for as long as our civilization endures. They discovered the wall of fire, They crossed the boundary of our solar home. They showed us where we live in the cosmos, and they proved that humans can build machines that last that function for decades in the harshest environment imaginable and that our reach can extend far beyond our grasp. Let's step back for a moment and consider what the Voyager mission and the Wall of Fire discovery teaches us beyond the specific scientific findings. What Voyager teaches us about exploration. First, vision matters. The Voyager mission was conceived when computers filled entire rooms, when no spacecraft had yet visited the outer planets, when the idea of reaching interstellar space seemed like pure fantasy. Yet engineers and scientists dared to dream big, to design for the longest possible mission duration, to build in redundancy and robustness. That vision paid off. A mission designed for a 4-year primary mission has now lasted 49 years, more than a decade longer than its designers lived. Second, we can't predict what we'll discover. When Voyager launched, the heliopause was a theoretical concept, barely understood. The Wall of Fire was completely unexpected. Many of Voyager's most important discoveries, Io's volcanoes, Europa's ocean hints, Neptune's supersonic winds. The structure of the heliosheath weren't even imagined when the mission was planned. This is the power of exploration. You discover what you don't know you're looking for. Humanity's reach beyond the solar system. Voyager represents humanity's first tentative step beyond our solar cradle. It's humbling and awe-inspiring simultaneously. Humbling because, in nearly 50 years, traveling at 38,000 miles per hour, Voyager 1 has covered only 0.02 light-years, less than 1/400th of the distance, to the nearest star. At its current speed, Voyager 1 would take 80,000 years to reach Proxima Centauri. We have barely left home, but also inspiring because we did it. With 1970s technology, we built machines that have operated in interstellar space for over a decade. We've touched the realm of the stars, however tentatively. We've sent our greetings into the cosmic ocean. The importance of long-term scientific missions. Voyager demonstrates why long-term missions matter. The most important discoveries often come not in the first flush of mission excitement, but years or decades later, when patience and persistence reveal patterns invisible in short-term observations. The Wall of Fire discovery required decades of data. The persistent plasma oscillations in interstellar space were only noticed after years of measurements. Understanding how the heliosphere changes with the solar cycle requires monitoring over multiple cycles, decades of observation. Short missions provide snapshots. Long missions provide movies revealing dynamics, processes, and changes that snapshots miss. Voyager as ambassadors of Earth. Each Voyager carries its golden record, a time capsule of humanity from 1977, when the Cold War divided the world, when the internet didn't exist, when climate change was barely discussed. Yet the message on those records transcends 1977. It speaks of a species that creates music, that contemplates the cosmos, that seeks connection beyond itself. Carl Sagan wrote, "The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space." But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The legacy that will outlast humanity long after the last Voyager signal fades, long after the spacecraft lose power and tumble blindly through space, long after human civilization has either spread to the stars or vanished from existence. Those two small spacecraft will still be out there, drifting through the galaxy, carrying the golden record stories of who we were, what we loved, what we dreamed. They are, in the most literal sense, our legacy to the universe, messages in bottles cast into an ocean so vast that they may drift for billions of years before anyone finds them, if anyone ever does, and yet we sent them anyway. That, perhaps, is the most profound lesson of all. We explore not because it's practical or profitable, but because it's in our nature to wonder, to seek, to reach beyond ourselves toward the unknown. We've traveled together today from the launch pads of Cape Canaveral in 1977 to the lonely depths of interstellar space in 2026 following, to tiny spacecraft on an incredible journey that continues even now. Let's recap the most mind-blowing discoveries. The wall of fire, a superheated plasma region, at 30,000 to 50,000 Kelvin, marking the boundary of our solar system. The heliopause crossing humanity's first entry into interstellar space, confirmed by both Voyager spacecraft at slightly different locations, higher temperatures and densities than predicted, revealing that our theoretical models were incomplete and that reality is more extreme than we imagined. The heliosphere as cosmic shield protecting all life in the solar system from deadly galactic radiation, persistent plasma oscillations, the hum of interstellar space, continuously measured for the first time, magnetic mysteries, unexpected field alignment that challenges our understanding of how solar and interstellar magnetic fields interact. What it represents. The wall of fire isn't just a scientific curiosity. It's the boundary of our cosmic home, the edge of the protective bubble within which all human history has unfolded. It reminds us that we live in a vast, hostile universe, shielded by an invisible magnetic cocoon created by our sun. It shows us that even at the edge of our solar system, nature can surprise us with extremes we never anticipated, and it demonstrates that we have the capability, the vision, the engineering skill, the patience to explore even the most remote regions of space and return knowledge that transforms our understanding. Why this matters for everyone. You might think this is just for space enthusiasts or physicists, but you'd be wrong. Understanding the heliosphere affects future space exploration. Every human mission beyond Earth orbit must account for this radiation. Environmental planet's protection. Knowing how our cosmic shield works helps us understand what makes Earth habitably a place in the universe. These discoveries redefine what the solar system means. Human achievement. Voyager proves we can accomplish extraordinary things when we commit to long-term vision. If you've made it this far, I have a favor to ask. Hit that like button right now. This video took enormous research and production effort, and your like helps it reach other people who care about space exploration. Subscribe to the channel if you haven't already. We're building a community of curious minds who want to understand the universe, and you're invited to be part of it. Share this video with someone who would appreciate it, a friend who loves space, a family member who's curious about science, a student studying astronomy. Help spread the wonder. And turn on the notification bell so you never miss an episode. We're covering the most exciting discoveries in space science, and you don't want to miss what's coming next. Now I want to hear from you. What amazes you most about the Voyager mission and the wall of fire discovery? Is it the extreme temperatures? The fact that machines built in the 1970s still work nearly 50 years later? The idea that we've sent messages to potential alien civilizations? The heliosphere's role as our cosmic shield? Drop a comment below and let's discuss. I read every comment, and I love hearing your perspectives and questions. Coming soon on this channel, we'll be covering the latest discoveries from NASA's James Webb Space Telescope, the incredible findings from the IMAP mission's first year of operation, and updates on plans for the proposed interstellar probe. Thank you to everyone who supports this channel, whether through Patreon, YouTube memberships, or simply by watching and engaging. You make this possible. Right now, as you watch this video, Voyager 1 and Voyager 2 are speeding through interstellar space at 38,000 and 34,000 miles per hour respectively. They're alone out there, the only human-made objects in the space between the stars, billions of miles from home, operating on decades-old technology, powered by decaying plutonium, transmitting whisper-faint signals across a gulf so vast it takes an entire day for their messages to arrive. They've already traveled farther and lasted longer than anyone dared hope. They've discovered things no one predicted. They've crossed boundaries thought unreachable. They've redefined what the edge of the solar system means. And they did it all to satisfy one uniquely human trait: curiosity, the desire to know what's out there, beyond the horizon, beyond the known, beyond the edge of everything. That curiosity built Voyager. That curiosity drives all exploration. That curiosity defines humanity at its best. And that fire of curiosity, that eternal human drive to explore, burns brighter than any wall of fire at the edge of the solar system. Until next time, keep looking up Keep asking questions and keep exploring.